so we're back. We got week 6, video number 2 now. The last video we talked about Lewis structures, which are 2 dimensions. Those are all done on paper. This video talks about Vesper theory. I'll tell you what it means, and it's how molecules actually look. You cannot do Vesper theory until you have the Lewis structure finished and in front of you. Okay, that's why this is video number 2. You have to have the Lewis structure. So this is molecular structure and molecular geometry, Vesper theory. I'll tell you what it stands for in a second. Molecular geometry is the 3D arrangement, 3 dimensions, 3D arrangement of a molecule's atoms in space. Okay, Vesper theory. So chemical formulas are great. We used these to make our Lewis structures, right? Counted up the valence electrons and did stuff like that. We've got our final structure. So chemical formulas allow us to draw Lewis structures. And we did that in week 6, video number 1, the last video. Allow us to draw Lewis structures. But Lewis structures are limited in that they really only show us the proper connectivity. They show us how the atoms are connected, where the lone pairs are. They don't show us about how the molecules really look in 3 dimensions in real life. So chemical formulas and even Lewis structures to a certain extent reveal little about the 3D geometry of a molecule. Vesper theory reveals this information. Okay, so Vesper theory, capital V-S-E-P-R, what is this? Vesper theory stands for valence shell electron pair repulsion theory. Basically, it's this. If you draw a single dashed line, that's 2 shared electrons. That's 2 electrons. Those 2 electrons are not going to like a neighboring bond because that's also 2 electrons, and electrons are both negative. They're going to repel each other. They want to get away from each other as best they can, and they can do this well in 3 dimensions, much better than they can on paper. So Vesper theory accounts for molecular bond angles. Because there's repulsion between shared electron pairs, or bonds, dashes, if you will, the atoms around the central atom tend to be as far away from each other as possible. All right, so Vesper theory accounts for molecular bond angles, and because there's repulsion between shared electron pairs, the atoms around the central atom tend to be as far away from each other as possible. These 2 examples, there's no real central atom, so we've written them the only way we can. HH, HCl. Notice that Cl needs an octet. Both are linear because there's no other way to draw them. If you have just 2 atoms connected to each other, of course they're going to be linear. So the molecular geometry for these guys is linear. All right. Now let's actually get to central atom here. Okay. So top of page 2 with our notes. Now we're really going to start to get going here. It says now with a central atom. So example, BH3. BH3, if boron is 3 electrons, group 13, hydrogen, group 1, 1 electron. We have a total of 6 electrons. Most of you know how to get this Lewis structure. How come boron doesn't have 8? It's one of the exceptions. It likes to have 6 electrons. Okay, the most famous exception is hydrogen. He likes to have 2 electrons, right? Now, in Lewis structures, we just put the H's top, right, left, or top, bottom, right. We don't worry about it, but the shape actually requires the hydrogens to have a 120-degree bond angle. That's the best you can do. So the molecular geometry for this is called Trigonal Planar. Kind of looks like a Mercedes-Benz logo. This is called Trigonal Planar. So the shape of this is Trigonal Planar. All right. Now, I don't even have to go out of the plane of the paper. Those bonds still look like the bonds I drew for Lewis structures. Example for CH4, 8 electrons. I have to go when you have 4 attachments. In this case, I have 4 hydrogens attached. You have to break the plane of the paper and go into 3 dimensions, which means I have to make my bonds look different when I draw them. So the shape of this has got 4 substituents. So the first hydrogen up, second hydrogen bottom right. Now I have a wedge coming out and a dash going back. So the dark wedge is a single bond coming out at me, and the dash is a single bond going into into the paper or behind the page. So this looks like a tripod. Okay, it looks like a tetrahedron. So the molecular geometry for this is tetrahedral. Now, you see I've highlighted here that the wedge comes out at you and the dash goes back. This is extremely important that you learn how to do this properly. Notice that I have my wedge going out, coming towards me, and it's going downwards. I've also got the dash line going downwards. So I've got this kind of tripod look with one more going up. Okay, so you draw the first two in the plane of the page. The third one you wedge out. The fourth one you dash back. All right, that's very important. You do that every time with 4 attachments, and the attachments don't even have to be atoms. For CH4, all 4 attachments were atoms. For NH3, it's going to look almost identical to CH4, but it's not going to seem like it's identical. So the Lewis structure is that first box there. We learned how to do this in video number 1. That's my Lewis structure. I just stuck them wherever I wanted. I didn't worry about valence shell electron pair repulsion. Now, shape, 4 substituents, just like last time. 3 atoms in 1 lone pair. So start by writing the nitrogen, of course. Now I have 4 attachments, 3 hydrogens in the lone pair. I always put the lone pairs in first because I got 2 spots where they can stay in the plane of the paper, up and to the bottom right. So this has a tetrahedral arrangement, but we don't call it tetrahedral. Imagine putting your thumb over the lone pair. The molecular geometry on this one says here, don't consider the lone pair. So I can't call it tetrahedral again. I'd call this one trigonal pyramidal. Trigonal pyramidal is when I got 3 atoms attached and 1 lone pair, okay, an electron pair. All right, the bond angle here is a little smaller. It's not 109.5, it's 107. That's because the lone pair up there is kind of like a cloud, and it's going to collapse the umbrella down of those HNH bonds. So the bond angle is less than 109.5 because the lone pair of electrons collapses the umbrella a bit. It's kind of like taking a tripod of a camera and closing it up a little bit to make the thing taller. All right, third example on Vesper theory is H2O. So we go through the motions, we get our Lewis structure. Lewis structure, you have oxygen in the middle. You think symmetry, put the hydrogens on the outside, 2 lone pairs. And we have 2, 4, 6, 8. Everyone's happy. There's my Lewis structure for water. Okay. Now the shape is, how many substituents do we have? How many attachments? 4. 2 obvious ones are the hydrogen atoms, but we also have 2 other attachments. There's 2 lone pairs on the central atom also for a total of 4. Okay, so I have to do 4 attachments is that tetrahedral arrangement. So I'm going to use the first 2 positions, which are in the plane of the page, to put my lone pairs in, and you'll see that when I get set up here. Oxygen, lone pair on the top, lone pair to the bottom right-ish, okay? And then I'm going to wedge my hydrogen out, and then I'm going to dash my hydrogen back. So if those lone pairs were atoms, this would look just like CH4 and NH3. But I can't call it tetrahedral because it's not 4 atoms. Can't call it trigonal pyramidal because it's not 3 atoms. It's only 2 atoms. So you take your thumb, cover the lone pairs, and this has a molecular geometry or a shape of bent. Okay? Some other people call it V-shaped. We're going to call it bent. Now this bond angle is 104.5. As you add more lone pairs, right? CH4 was 109.5 bond angle. Then we have 107 bond angle. Now we're down to 104.5. Just those electron pairs are just really collapsing that umbrella down, if you will. Okay? So bond angle is 104.5. It's less than both 109.5 and 107.5 because now we have 2 lone pairs collapsing the umbrella even more. And I've drawn a little sketch here just to show you how we're really closing in. Okay, so that was how we do that for H2O. And our next example is SO2. Okay, so SO2, we got basically 3 guys in group 16, sulfur and oxygen. We came up with 18 electrons, and the Lewis structure for this is a double bond. So this is my Lewis structure. Okay, so I don't need to worry about the double bonds being any different. I just treat it as if it's a single attachment, because it is. It's a sulfur attaching to one oxygen, just happens to be a double bond. Okay, so how many things are around sulfur? It's the central atom. The central atom sulfur has 3 attachments. It's got 2 atoms, each oxygen, and then that 1 lone pair on the sulfur. So how do we do 3 things? Well, it's kind of like BH3. We can stay in the plane of the paper for 3 attachments. All right, so I've got my sulfur. I like to do my lone pair first, my double bond to the bottom left, single bond to the bottom right. This is sort of like BH3, except one of my H's is a double bond, is a lone pair. So this is not a trigonal planar molecular geometry or shape. It is bent, right? And again, we ignore the lone pair when we write down the name of the molecular geometry of the shape. All right. So the bond angle for that one, well, BH3 was 120. The bond angle for this guy is less than BH3's 120 because we have that lone pair up there kind of collapsing down my 120-degree bond angle. So the bond angle for OSO is less than BH3 bond angle of 120 because the lone pair on sulfur collapses the OSO bond a little bit. Now, did I treat this double bond any differently than I would a single bond in Vesper theory when I was coming up with the shape in the molecular geometry? I did not. So the shape is an actual drawing. Molecular geometry is a name. The molecular geometries we need to know are linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. All right? All right, so that's it for this video, and that is it for Lewis structures and Vesper theory. And the next thing we will start to talk about is an entirely different subject. So that's all you need for Lewis structures and Vesper theory and how to draw molecules properly, all right? All right, so I'll see you in the next video.